Okay, so today's notes are on 7.4a. The properties are laws of logarithms, and our content objective is to use the properties of logarithms to simplify expressions, and our language objective is to use the correct terminology to explain the properties of logarithms. I will probably refer to them as laws of logarithms throughout the notes and in the future because I prefer to call them LOLs or laws of logs, but let's talk about what those are before I get into what we're going to call them. So the properties or laws of logs, like I said, I call them LOLs, are pretty cool because they're actually just the inverse of our laws of exponents. So we will start with the product property. And this says that if I have a log with a base of b and I'm multiplying two things in the argument, so I have m times n in the argument, I can rewrite that as two things or two logs being added. So log base b of m plus log base b of n. I think this is really cool because this is like, if you remember our laws of exponents, if I'm multiplying two things with the same base, I add their exponents. And that's pretty much what we're doing here. If you remember, logs represent exponents, or they calculate exponent values. So if I'm multiplying two things inside that have the same base, then I can add them. So it's pretty much the inverse, which makes sense because logs and exponentials are inverses. So it's the inverse of the exponential property. So again, if you're multiplying in the log, you add the two, you can separate it into two logs being added. And the same goes the other way. So if you are adding two logs, you can rewrite it with them being multiplied in the argument. This similarly applies to the quotient property. So if you remember from our laws of exponents, if I'm dividing two things with the same base, I can subtract their exponents. So if I have two things in the argument of my log, I can subtract the two separate logs. So if I'm dividing in my argument, I can subtract, and vice versa if I'm subtracting two logs, as long as they have the same base. So this is crucial. This only works if they're the same base, just like our laws of exponents. But if I'm subtracting two logs with the same base, I can subtract or divide their arguments. And last but not least, this one's going to be super important, the power property. So if you remember from our laws of logs, if you are raising a power to a power, then you multiply with our laws of logs. So similarly here, if I have an argument with an exponent, so the n in this situation is an exponent, so if I have m to the power of n, I can rewrite that as n being multiplied by log base b of m. So I'm allowed to sort of drop this to the front or bring this to the front and multiply them because my power rule for exponent says when I raise a power to a power, I multiply them. Same thing applies here. Since logs calculate exponents, I'm raising it to a power, I can multiply them. This is actually going to help us solve later on, so keep this one in mind. It's going to be particularly important. Before we get into how we're going to use that to solve, we'll do that in our next lesson. We're going to talk about how to simplify using these new properties or laws. So we're going to simplify or write as a single log. And we have log base 4 of 32 minus log base 4 of 2. So our first step here, we're going to rewrite using the laws of logs, or properties of logs. I'm going to abbreviate them to LOLs, laws of logs. And I want to make sure we check to ensure that they have the same base. Because again, these laws only work if I have the same base for both of them. So since they both have a base of 4, I can rewrite it using logs. Since I'm subtracting these two logs that have the same base, I can use my quotient property and rewrite them in a single log being divided. So now I have log base 4 of 32 divided by 2. So again, I'm taking the arguments and dividing them. And then I'm going to simplify. So when I simplify that, 32 divided by 2 is 16. So I have log base 4 of 16. And we know from our previous lessons how to evaluate this. So I'm going to do that as my final step so I can fully simplify it. I can do more than just write it as a single log. I can fully simplify. So if you remember, what we do is rewrite this as an exponential. So 4 to the what will give me 16. And so we can say 4 to the second. So log base 4 of 16 is 2 because if I solve this, I know that's going to be 2. If you rewrote it as x equals 2, that's fine, but make sure 2 is actually your only answer since there was no x in the original equation. So let's do some quick checks. I'm going to give you 2 to do the same thing for, so simplify or write as a single log. So I have 6 log base 2 of x plus 5 log base 2 of y. And then my second one, I'm going to fit this on the side here, is 2 log base 4 of 6 minus log base 4 of 9. So that's a base 4. That one's a little squished, sorry about that. Try those on your own using these laws. I'm going to go over them now. So for this one, I'm going to start by bringing up the number in front to the exponent. So I'm going to rewrite this as log base 2 of x to the 6th plus log base 2 of y to the 5th. So again, since I was multiplying, I'm doing this in the reverse order of what we did here. So since I was multiplying, I brought it up into the exponent, which I'm allowed to do using the power property. Now that I see that I'm adding 2 logs of the same base, I know I'm allowed to multiply the arguments using the product property. So I'm going to say log base 2 of x to the 6th, y to the 5th, and that's all in one. You can put parentheses around it or not. It's fine either way. And that would be our answer because there's nothing I can really evaluate at that point. So that would be our solution for our first one. The second one, I'm going to start by doing the same thing. So sorry, I'm going to sort of slide this to the side, but I'm going to bring the 2 up into the exponent. So it becomes log base 4 of 6 squared minus log base 4 of 9. Again, since I'm subtracting 2 logs with the same base, I can divide their arguments. So I have log base 4 of 6 squared, which we know is 36 over 9. If I simplify that, I get log base 4 of 4, which 4 to the what gives me 4. It's going to equal 1. There's a few different ways you can think of this. The 4s, they're inverses, so they cancel, or you know the exponent here is 1. So you know 4 to the 1 equals 4. A few different ways you could evaluate that if you rewrote it as an exponential and calculate it out. But your answer for number 2 is 1. All right, make sure you write some questions on that. I'm going to flip the page so we can practice going the other direction. So hold on just a second. We're going to do another quick check, but we're going to go the other way. So I want you to write this in expanded form. So we practice simplifying. Now I want you to practice going the other way. So the first one I want you to do is log of 4x over y. And again, if there's no base, it's implied a base 10, a common log. And the second one is log base 9 of x to the 4th over 729. All right, try those out on your own. I'm going to go over them now. So again, since I'm dividing in my argument, I know the quotient property tells me I can rewrite those as 2 logs being subtracted. So log y. And you can actually go even further with this because I'm multiplying those 2 numbers in the argument. I can rewrite this as 2 logs being added. So I'm going to simplify or expand this even further. I have log base 4 plus, or sorry, log base 10 of 4 plus log base 10 of x minus log y. And that is my fully expanded form for that log. All right, the next one, I'm going to similarly start by subtracting 2 logs of the same base since I'm dividing in the argument. So I have log base 9 of x to the 4th minus log base 9 of 729. Since I have an exponent on this, I know I'm allowed to bring that to the front using the power property. So I have 4 times log base 9 of x minus, I can evaluate this log here because actually 9 to the 3rd is 27. So if you evaluated this log, I can do it up here, 9 to the x equals 729. I know x would be 3. If you use your little power or paper or your powers of small integers. So I can actually rewrite this whole thing as just 3. And that would be my fully expanded form of that log. Make sure you write down any questions on that. There's one last thing I want to go over for these notes, and it's the change of base formula. Sorry, one second. So change of base. And this, the general formula for this is for any positive numbers, M, B, and C, where, or with a value of b that does not equal 1, and a value for c that does not equal 1, then I can say log base b of m is equal to log base c of m divided by log base c of b. So this might seem confusing, but what this means is if you have a base here that you don't know how to work with or you don't want to work with, you can change the base of it by rewriting it with a new base as long as you're dividing by a log with the same base of your previous base. That sounds really confusing, but we're going to go over some more specific examples. But this is going to be particularly useful when entering into a calculator. The reason I say that is because if you haven't noticed, most of the calculators we have do not allow us to change the base of our logs. It provides two logs with different bases. It provides the common log or log base 10 and ln, a log base e. So if you have any other log like a log base 9 or a log base 4 or log base 2, then you're not going to be able to enter that in your calculator. And if it's not going to be an even or a whole integer, that can be difficult to calculate at times. So I'm going to show you how this is useful. So our first example, I want to evaluate log base 81 of 27. And this one actually you could do out algebraically. So I'm going to show you three different methods for doing this. We'll start with method 1. This is probably what we've been doing previously. So if I wanted to evaluate log base 81 of 27, I would say, okay, well that equals x. I can rewrite this as an exponential. So I have 81 to the x equals 27. I can rewrite these with the same base. So I'm going to rewrite this as 3 to the 4x equals 3 to the 3. Then I can set the exponents equal and say 4x equals 3, so x equals 3/4. So 3/4 would be my answer for that particular one. Method 2, if I had log base 81 of 27, I can use this change of base formula. So this is where I'm using the change of base formula. And the way I do that is if I wanted we can do it algebraically without a calculator first. So I know that these are both powers of 3, so I could rewrite it log base 3 of 81, or sorry, 27. Oh, sorry, 27 over log base 3 of 81. So again, this is how you use the change of base formula. You can make up any base you want to become c as long as c is positive and not equal to 1. But since they're both powers of 3, I'm going to choose log base 3, and then I put what the original argument was in the numerator, the original base in the denominator, and then I can simplify them similarly. So this becomes log base 3 of 3 to the 3 over log base 3 of 3 to the 4. And again, if you evaluate these, this just becomes 3 to the 4th. So 3 to what power gives me 3 to the 3rd? 3. 3 to what power gives me 3 to the 4th? 4. So it's just 3/4. The last method, method 3, is the one that's going to be useful, especially when these don't work out evenly with whole numbers. It's, again, using the change of base formula, but you can make it any base you want. Sorry, that's a 2, 27 again. So I would rewrite this using a common log base. So instead of choosing log base 3, I'd use log base 10, which is in my calculator, the common log, or ln, which is log base e. And then I do the change of base formula the same way. So since I didn't write anything, my implied c value is 10. And if I plug this into a calculator, I don't have one right next to me right now, but I'll show you in class. If I plug in log 27 divided by log 81, it's going to give me 0.75, which I know is equivalent to 3/4, which is my answer. So 3 different ways you can solve this type of problem. One we've done previously, and then 2 new ways using our change of base formula. As long as you can do this way and the calculator way, you should be okay in most situations. So as long as you can do these 2, you should be good, but make sure you write down any questions, comments, or concerns you have so we can go over it in class. I'm going to do one quick check because I think we have a little time. I want you to do the same thing, but evaluate log base 5 of 36. And you're going to want to use your calculator for this one if you have one with you. If not, you can wait for me to go over it. But to solve this, I would rewrite this with a log base 10 or a ln. So I'd do log of 36 divided by log of 5. So again, the argument goes there, the original base goes there. If I plug that into my calculator, I get approximately 2.226 and so on, which rounds to approximately 2.23. And that would be my answer for that log. So again, especially when it doesn't work out with pretty numbers, this is a great method to use to solve on a calculator. All right, that's all for today. See you guys in class.